So I apologize in advance because this is going to be a linear solver talk.
What are the best talks?
So as a motivating example, let's jump right in. Let's look at a sort of two-temperature PDE model where you've got a heat conduction equation for this electron temperature, T sub E. And you also have a heat conduction equation for a lattice temperature, T sub L. And at initial glance, these basically just look like two Poisson equations. But they're coupled through this temperature difference term where there's this parameter G. And if a user takes G and cranks it up, then those two sort of become really tightly coupled. So how do we actually end up solving this system? Well, before I started to investigate all of this Teko work, what we would do in Sierra thermal fluids is just use a domain decomposition approach where we split it into subdomains that are processor local. Then we do some kind of incomplete LU factorization to solve it. And I'll refer to that as DDILU. We could also use Teko to create a block-based Gauss-Seidel approach. And so in this example, I'll use MueLu with smoothed aggregation for both of the blocks with a Chebyshev smoother. And now if we define a dimensionless coupling parameter eta, which depends on the coupling strength G, then I can look at different coupling regimes where if eta is quite small, then T and E, then the electron and lattice temperatures are largely independent. But if they're really tightly coupled, then those two temperatures will be similar. And so now let's sort of consider a toy example where I take G to be 10 to the fourth. I solve it using finite elements on just the unit square. And I just use homogeneous Dirichlet boundary conditions. And so this is what that actually looks like. So I have plotted here on the y-axis, this is my relative residual. And on the x-axis here is my iteration count. And so if we start with the domain decomposition-based approach, we see it doesn't converge after 200 iterations. In fact, we're pretty far away from our desired convergence tolerance. With block Gauss-Seidel, it takes like 80 iterations. It's not great. So what I'm going to be talking about is this method over here on this green line, which converges in fewer than 25 iterations. And how is it that we actually accomplish this? We accomplish this by using a monolithic block algebraic multigrid technique, which this already exists inside MueLu. But I'll note that there are a couple of limitations to what is currently in the developed branch right now. Firstly, I'll say that the syntax is locked behind the sort of expert MueLu XML syntax, which I am not smart enough to comprehend. There is little interoperability between using block and non-block based smoothers. So right now, if you wanted to use a monolithic DDILU smoother with this approach, you're just out of luck. And then it is possible to incorporate per physics information like coordinates or material properties, but it's challenging to configure. And so what I actually want, if I put on my actual Sierra developer user hat, like user of Trilinos hat, I want to be able to specify independent coarsening per physics. So for example, maybe I use smoothed aggregation on one block and Petrov-Galerkin on another block. I want to have first-class interoperability with Teko. That means I want to be able to both use this in Teko and also use Teko as a smoother inside this. But then I also want support for monolithic smoothing approaches, where I can actually use a domain decomposition approach as a smoother on the monolithic system. And then lastly, I also want to be able to incorporate all of the per physics fields that end up being useful. So the approach I'm going to take, and this is kind of the standard approach with a lot of these block-based algebraic multigrid techniques, is you've got some matrix A, and if you look under the hood at what A is, it's an n by n system where each of the entries in the matrix is itself a matrix. And so each one of these blocks on this main diagonal correspond to an individual bit of physics, like Poisson or advection diffusion, and the off-diagonal blocks correspond to coupling. Well, if you know anything about algebraic multigrid methods, you know that once you have a prolongator and a restrictor, that gives you a way to generate a coarse grid operator. And so we're going to generate those for all the various levels, and I will get into that shortly. Once we have that in place, we can then construct our smoothers, which include both block-based smoothers provided by Teko. These include things like block Gauss-Seidel or block Jacobi, where we take individual smoothers for each of the physics, and we piece them together into a monolithic block smoother by incorporating them through this block-structured matrix. But then we also want to be able to support monolithic smoothing, so like using DDILU on the entire thing, or for symmetric positive definite problems, we could just use Chebyshev polynomial smoothing everywhere. And so one thing now that we have to consider is the question of, I run MueLu to get my algebraic multigrid cycles for each of my physics, but what if the number of levels doesn't match, right? So in this example here, guy on the left, he has 3 levels, guy on the right only has 2 levels. Well, we can either use the maximum across all of them and accomplish that by creating a sort of fictional coarse grid over on the right, or we can do the minimum and essentially truncate at the second level and treat this guy in the middle as our coarse grid. And we want to be able to support both because it can be useful in different use cases. This is all just sort of plumbing to sort of put into math what I'm trying to do here, where I define a common depth as being either the minimum or the maximum over all of the subblocks. And then if needed, if there's a sort of fictitious one, then I need to just use the identity matrix for my restriction and prolongation operators. And then the same matrix becomes my coarse grid there. And then once I have these per block prolongators and restrictors, I then get the monolithic ones by taking this this block diagonal system where each of these individual prolongators and restrictors corresponds to each bit of physics. So for example, P1 could be something that is designated for Poisson, and P2 could be something that is for an advection diffusion equation. Once I have all of that in place, everything else sort of follows the standard algebraic multigrid V cycle, where you do some smoothing, compute your residual, then go onto the coarse grid, do that solve. Once you get the coarse grid back, you prolongate it back and do a smoothing. And then once you're at the bottom of the level, you actually do the coarse grid solve. Jonathan?
Maybe you're going to get to this, but in the case of like when you're using the identity, are you doing extra work or are you doing something smart to avoid that?
So that is actually at the user's discretion at the moment. So one option, for example, is to just do absolutely nothing when it comes to doing the smoothing, and you basically just carry those degrees of freedom through until you get to the coarse grid solve. So that's a common use case right now. Yeah. But it's all configurable at the moment. So let's look at a couple examples here. So this example is a steady two-way couple thermoelasticity equation with advection, where I solve for linear elasticity, but there's a temperature coupling. And then for the temperature equation, we'll use advection diffusion heat equation, where I'm solving for the temperature. There includes a coupling with the elasticity solve, and we also include a user-prescribed velocity field, too. So now we can consider a specific example of this where we crank up the coupling between the two. We look at that same unit square domain, and let's just pit several different preconditioners against each other. So DDILU with fill and overlap equal to 1. Block Gauss-Seidel, where for the elasticity solve, I use a MueLu setup that is appropriate for elasticity. And for the temperature, I will use scalar AMG, which for the prescribed velocity field I'm using while it is asymmetric, it's not so asymmetric that I can't use smoothed aggregation. And for that, I'll actually use DDILU with fill and overlap equal to 1 as a smoother in this case. And then lastly, I'll consider a monolithic AMG approach, but I'll use a block Gauss-Seidel preconditioner, where I use Chebyshev for the elasticity part and DDILU for the temperature part. And so here's what the results actually look like. The first thing I want to note is if you were ARIA 4 years ago, you would be on this blue curve here, right? You'd make absolutely no progress on your solve. So what you would do is you'd go back and you would start to crank these up until you basically prayed, please solve this. And if you were really desperate, you would just go to KLU2 and suffer the consequences. Thankfully, right now in ARIA, we have this orange curve available to us, which is all through Teko at the moment, to use the block Gauss-Seidel. But it's over 100 iterations. That's kind of expensive. So what we really want to do is be on this green curve here, which is like almost a factor 2 reduction in the iteration count. So I'll move on to one final example, which is a steady linear drift Poisson-Nernst-Planck equation, where you have a Poisson equation for the potential field, which is coupled to a concentration term. And this concentration term is described by the Nernst-Planck equation, which follows this steady conservation law, includes a coupling to the potential equation from above, and also includes a prescribed user velocity u. And so the A11 block, which corresponds to Poisson, that's symmetric positive definite. We can just use SA AMG or smoothed aggregation. But for the A22 block, that can actually be really asymmetric. And in fact, it obeys this sort of mesh Peclet number condition, which depends on this D parameter, which corresponds to the diffusivity. And in a lot of real-world applications, that diffusivity is really small. And so it drives that mesh Peclet number quite large. If you also do a mesh refinement study, that also drives the Peclet number quite large. So that advection diffusion block for the concentration ends up becoming really asymmetric. So it is not a good candidate for smoothed aggregation whatsoever. So we're going to note that when we design our preconditioners for this study. Again, I'm going to include DDILU just for reference. And then I'm also going to include block Gauss-Seidel, where I will use smoothed aggregation for Chebyshev. And then I found that I actually got better performance using DDILU for the concentration block M22. And I did not have much luck with the Petrov-Galerkin in that case. But when I actually went to the monolithic system, I got really good results using Petrov-Galerkin. And this is actually a use case where using a monolithic smoother, so even though I'm taking advantage of all this block structure, I still want my smoother to be able to sort of include that coupling. It ends up being really effective in this particular use case. So again, if you're ARIA circa 5 years ago, you're on this blue curve here, which does not converge. If you're ARIA today, and you kind of extend that line out, you can converge in 225 iterations or so. And then with this proposed change, that's like a 10x reduction in the iteration count. And I'll note that these parameters that I have here, this is kind of a not worst case scenario, because this F here actually corresponds to Faraday's constant, and Z is just an integer. So this guy can be really large, and as it goes up, the coupling between the two blocks becomes really strong. But in short, by sort of using this monolithic algebraic multigrid approach, I can really hammer down the iteration counts. And so I just wanted to demonstrate that this approach outperforms the one-level block-based methods for all of the cases that I showed. And this already extends the capabilities in MueLu. So all of this was just a little bit of development work to get the pieces that were already there correctly glued together. There's some logic to automatically switch between the block representation and the assembled T-Petra representation. And there are a few mild limitations that are needed at the moment. We can probably go through and address all of these at some point. But in short, if you want to look at the specific changes, the pull request is over on the left. And if you want to look at the multiphysics examples, that's on my GitHub on the QR on the right. And with that, I will open the floor to any questions. Jonathan?
So can you go back to the last convergence plot?
Mm-hmm.
The monolithic in this case, you're doing, I guess you're doing SA and Petrov-Galerkin for the coarsening.
Yeah.
And are you using DDILU on
Yeah,
levels?
on each level. Yeah.
And is it necessary on all levels?
So that is not something that I investigated too much. What I will say is my initial attempt was to use the block Gauss-Seidel noted here, but with a Chebyshev smoother, and use that guy as a smoother. But I actually got better convergence, like significantly better convergence, by using a monolithic smoother here.
Yeah. I mean, I guess Chebyshev would kind of choke on the 2-2 block.
Right. So if you were to use like Chebyshev monolithically, that wouldn't work. If you were to use Chebyshev on the A22 block, that also wouldn't work.
Right. But you did, but your first bullet, you did DDILU.
Yeah.
That's just like a fine grid smoother. And that,
Yeah.
it converged but really slowly. Is that, you have that on the next plot, right? On the next slide?
Yeah, so the orange curve, that is this block Gauss-Seidel approach, which is really just like a one-level block method. But inside of that, I'm using smooth aggregation on the 1-1 block.
Yeah, sorry, I meant the first square bullet, DDA1 ILU.
Yeah, that's just a one level on the entire monolithic system.
On the next plot, or in
It is. It's the blue curve
Okay.
up here at the top. And I'll also note, right, the smoother that I consider down here, that's the same guy as this guy,
Yeah.
right? But I'm just using him on each of the levels.
That's right. And so that next plot then makes sense because smoother is like it's doing something initially, but then it's
Right, right. But then it doesn't converge like that kind of long wavelength modes. I think Chris Seifert has hand up first.
Yeah, I've got two questions. So your DDIO uses the processor size subdomains, right?
Yep. Well, extended by 1 degree of freedom, but
Like you're
yeah.
not doing aggregate size subdomains, right?
Right. No, these are totally like processor local. And I should have noted all of these results are on 8 processors. There's very much like a toy problem. Yeah.
So second thing, and you might not see it as badly with the 2x2 matrix, but the transfers for like doing SPIMB and whatnot are not for blocks are not as efficient as they could be. Do you care?
We do care. At the moment, I don't have anything specific to actually address that issue, though. But so
I have ideas, so we should talk.
Okay. Yeah, I am interested because I am doing lots of scaling studies on these, and the strong scaling is very much a concern there just because of Amdahl's law. Like you have, right, you kind of have to serialize those. But there's maybe something that we can do to address that. Christian?
Yeah. Do you have some timing numbers? Because I mean, 10x is
Yeah.
versus like a single level.
Yeah, so I intentionally did not include timing numbers, not because they were embarrassing or anything, but because these are such like small toy problems that I felt like it would be somewhat disingenuous to even include them. So I will note this is all very much like a work in progress, but I'm hoping to get it into Trilinos and start to kick the tires on it in Sierra.
So, out of the results that you presented are key,
Mhm.
would you expect that preconditioning strategy to go in 3D cases?
That preconditioning would.
The strategy, like the ANG technique that you're using,
Yeah,
expect to see the same reduction in linear iterations for 3D cases?
Yeah, I would expect it to be largely similar for 3D. Again, this was really more of like toy examples, so that's why I limited myself to 2D. But I think it would also be the same case in 3D as well.
I think it would be harder though, maybe to, I mean, you might not see as dramatic a difference. You'd have to scale up.
Alrighty, any other questions? Let's thank Malachi.